All right. Hi, everyone. Let's do start unit 2 in Calc 2, which is going to be all about techniques of integration. Tons of different ways to do antiderivatives. That's what we're going to focus on. So starting off with 3.1, which is integration by parts. It's always good to remember where the technique comes from. So remember U substitution, when you let U equal something and then it changes the integrand, simplifies things. That was chain rule, but backwards. So if you remember chain rule for derivatives, U substitution was chain rule backwards, so antiderivatives. And so now we're going to do something very similar, but instead of chain rule, we're going to focus on product rule for a little bit. So here is the theorem and a formula. And you could, if you want, write that formula down and then memorize it, but that's no fun. Let's actually understand where it comes from. I think that's going to make a way easier to understand. So I'm going to start off with the product rule. So we're going to start off with trying to find, let's say, the derivative of two things multiplied together. So the product rule, let's just call those U of X and V of X, two functions multiplied together. Let's focus on what that product rule is. We remember it's going to be the derivative of the first one, leave the second one alone, plus the first one I leave alone times the derivative of the second one. So that is the beginning of the product rule. Okay, that's just the regular old product rule that we learned in Calc 1. Then we're going to try to think about ways to undo this. So we're going to kind of do a sort of derivative, or sorry, let's do, I should be more clear about that, an integral on both sides of that equal sign. Remember, whatever you do to one side, you have to do to the other side. So we're going to do an integral on both sides of that equal sign and see what happens. Over here on the left, you should notice that the antiderivative of a derivative is going to get you right back to where you started from. So U of X times V of X is what I'm going to be left over with there on the left side of that equal sign. And then on the right hand side, I'm just going to copy down the integral notation so we don't lose it. Oh, I should make that clear here. The integral of U prime of X times V of X dx plus the integral of U of X times V prime of X dx. Essentially, I just sort of distributed the integral across the plus sign, which we remember from Calc 1 we're allowed to do. Okay, so then we end up with this, and I want to kind of think about something here. There's a simpler way to visualize this notation so that we don't have to write down so much. So I want to give you a quick reminder maybe from Calc 1. Maybe remember Leibniz notation like dy dx or df dx, et cetera, or you could have used the f prime of x. That was one notation for derivatives. Then maybe you also remember differentials. So df and dx all by themselves are in fact their own differentials. This kind of came down from linear approximation. So if you wanted to go back into your Calc 1 stuff and think about linear approximation, that's where that came from. The only reason I'm bringing that up, though, is to simplify some notation. So instead of seeing this as v prime dx, I could just call that dv. All right, I'm using the letter v for the name of that function. Really, it truly doesn't matter so much. So the reason I bring that up is just to simplify the notation. So I got to give myself a little bit of space. I realize there's not quite enough space here, but that's okay. So I'm going to rewrite this then as just u times v equals the integral of, and then v times du plus the integral of u times dv. And I'm going to highlight a few things. If you're writing this down, that's great. I want you to write it down, but maybe pause for just a second and watch what I'm going to highlight. So it was this v prime dx that I just turned into the dv. Using the stuff I learned from differentials in Calc 1, just to simplify the notation. And then also what I decided to do, instead of u of x every time, we're just going to call it u. Okay, and then we keep going backwards here as well. So then instead of v of x, I just called it v. Okay, and then I also chose, instead of the u prime dx, that is just du, using the differentials that we learned from Calc 1. Okay, all that was just to simplify the notation. Okay, we still have the exact same equal sign, and I didn't do any calculus there. It's the exact same equal sign. I'm going to run out of space. I'm going to just rewrite that equal sign. So I have u times v equals the integral of v times du plus the integral of u times dv. I just copied it down. Now I'm going to rearrange my equal sign. And I'll kind of show that with a different color a little bit. There's more than one way I could rearrange the equal sign, but essentially I'm just going to take this integral and bring it to the other side of the equal sign. And if I do that, that's going to end up with a uv minus the integral of v du is equal to the integral of u dv. And then every equal sign can be read both ways, both directions. I could read that backwards. So I could rewrite that one more time and say the integral of u times dv is equal to uv minus the integral of v times du. That's the proof. Okay, that really is the proof. I don't know if you were paying attention, but check it out. That formula that I had typed up there, that was integration by parts. This is going to be a technique for integration. Now we've proved that formula. Okay, so now we have a formula. Cool. The hard part then is actually when do I use it and how do I use it? We have a formula. We've proved that it's a true equal sign. How to use it is going to be a whole other ballgame. So I'm going to leave that formula up there. Maybe I'll even highlight that simply because we're going to use this one a whole lot, not just in 3.1, but for the rest of your Calc 2 content. This is going to be everywhere. Okay, so we'll start simple. We're going to just start with this example. I've got like some part A, B, just multiple examples that we're going to do here. So this one is 2x times e to the 3x dx. This is the question I'm trying to find an antiderivative of. And if you think about everything you learned in Calc 1, I don't know the antiderivative right away. There is no product rule for antiderivatives. I can't do a u sub. You can try a u sub if you want. You are going to notice that because those two powers are the same, the u sub won't be helpful in any way. So I'm kind of stuck. So what I'm doing here, this new technique, is when you have a product and you realize that the u sub isn't going to work, any of your Calc 1 methods aren't going to work, then the next thing that you try is this integration by parts. So the integral of this product, we're going to try an integration by parts. So in order to do that, I have to label some things. The formula that I had there used the variables u and v. So I need to make a choice on what I want the u to equal, and I need to make a choice on what I want the dv to equal. That's important. So maybe pause and look at that formula one more time. This is the integral of u dv is on the left side. So whatever it is that I have right here, one of the pieces of my integrand is going to be u, and one of the pieces of my integrand is going to be dv. So that's what I'm making the choice of. So if I were to let that u be 2x and then dv be e to the 3x dx, then that means that this guy has become u times dv, which is what I have in that formula. So that's step one, is making a decision on your u and your dv. Step 2 is to fill in the rest of the formula. Okay, but before I fill it all in, let me read through what I need. I'm going to need a u, which I have, check. I'm going to need a v, which I don't have. I have to find it. I'm going to need a v. I'm going to have to find it. And I need a du, which I don't have. I'm going to have to find. So let me find what I need first, and then I'm going to fill in that formula. So you're going to need a du, and it's the same as it was for u sub. This is no different. The derivative of 2x is just 2. And don't forget your differential, just like we did before. Every differential needs that differential. And then I'm also going to need a v. So it's really important to notice that from u to du, I did a derivative. But now from dv to v, I need to do an antiderivative. So work backwards. So the antiderivative of e to the 3x is e to the 3x times 1/3. Remember that divide by the constant multiple. Now, technically there's a plus c, but we're going to do a plus c at the very end. So we'll just throw in the plus c at the very end. So you don't need to write that right now. Now I have all of the pieces that I'm going to need. Now I'm going to fill in my formula. So I'm going to kind of draw a little arrow over here, and this is going to equal uv minus the integral of v times du. That was the filling in the other half of that integration by parts formula. Now I'm literally going to plug and chug. So once you've done all of the decision making over here on the left, now you're going to do just a plug and chug on the right. We can do it. So u is 2x. So I just copied that down. Now v. V is 1/3 e to the 3x. So 1/3 e to the 3x minus the integral. Just copying it down. Okay, then I need a v. So v, do I have a v? I do. It's 1/3 e to the 3x. And then now I have a du, and my du I have is 2 dx. The differentials are vital. Make sure that when you're taking notes, you should be taking notes right now, every single equal sign, differential, integral, they're all important. Don't lose any of the notation along the way. Okay. All right, and now let's continue on with the simplification. This becomes 2/3 x e to the 3x minus, I'm just going to go ahead and factor out the constant multiple from that integral, which we're always allowed to do. And then I can finish off finally by actually doing this antiderivative. I still have an integral in the answer, and that's never good. You can't have an integral as an answer to an integral. That's never going to be good. So you have to keep going. So that 2/3 is going to stay. That negative 2/3 is just there. That's going to stay, no problem. Okay, and then I'm going to have to do the antiderivative of e to the 3x, which is 1/3 e to the 3x. Now I can throw in my plus c. And then, of course, we know what 2/3 times 1/3 is, so that'll just become the 2/9. Ta-da! All right, that's integration by parts. Let's practice again. Okay, multiple examples here. This is going to take a lot of practice. We just got to practice over and over again. So let's look at that part B of this example right here. So I've got the integral of x times sine of 2x. Again, I don't know that antiderivative off the top of my head. I could try a u sub, it didn't work. So what I need to do now is set up my integration by parts. The first thing that you do for integration by parts is you have to make a decision. Which one of those is going to be a u and which one of those is going to be a dv. So if I were to let my u be x, then dv is going to be sine of 2x dx. And then you do the derivative of one of them and the antiderivative of the other. So I had a u equals, now I had to do a derivative to find the du. Now I have a dv, I need to do an antiderivative to find the v. So an antiderivative of sine is negative cosine, but of course, don't forget to divide by that constant multiple, and we'll deal with the plus c later. Okay, all right, so we're doing pretty good so far. Then I'm going to have to set up my integration by parts formula. So I'm going to go ahead and do that. This is going to then become uv minus the integral of v times du. I just copy down the formula. This is not a formula that will be given to you on the exams. So you'll need to know this formula. This is going to be equal to x times negative 1/2 cosine of 2x minus the integral of negative 1/2 cosine of 2x dx. So my v was this guy, my du was that guy. Now I'm going to go ahead and simplify. Okay, I like to simplify those negatives. Clearly, two negatives are going to turn into a positive. I simplify first and then do the integral. If you try to do the simplification and the integral at the same time, you'll probably miss a negative. It's too hard to do them both at once. So do it one at a time, one at a time. So negative 1/2 x times cosine of 2x plus 1/2 times the integral of cosine of 2x dx. And then, of course, we know you can't have an integral in the answer to an integral. So now I have to actually do that antiderivative. And the antiderivative of cosine is sine. And, of course, divide by that constant multiple, which will make this now a 1/4 sine of 2x. Ta-da! Okay, so looking at just those first two examples really quick, I want to maybe pause here and think about the first step one more time. The first step for integration by parts, I said to you, was make a decision on what your u and dv are. How do I make the decision? Could I have switched it? I mean, sometimes, yeah, sometimes you can switch it. Sometimes it doesn't work well to switch it, though. So what I want to do is I'm going to give us a little bit of space really quick, and I'm going to give you an example of how to make that choice. There's more than one way to do it, but I'm going to give you a way to make it easier. So off here to the side, here's what I'm going to write down. Liate. Liate. This is going to be your choice for u. This is going to be the choice for your u equals. And I'm not going to talk about the dv. dv is the other one. Your choice for the u equals. L stands for logs. I stands for inverse trig. A stands for algebraic. T stands for trig. And E stands for exponential. So this is going to be your default go-to, how do I make a decision for my u equals? So if you have a log, that has to be your u equals. It'll never work the other way around. I can promise you that. And then if you don't have a log, then you move on to the next one. Okay, I don't have a log, but do I have an inverse trig? And if you have an inverse trig, that has to be your u equals. If I don't, then I move on. If I have an algebraic, do I have algebraic? I mean like x or x squared or the square root of x or x plus 5. That's what we mean by algebraic. If I have an algebraic, then that would be my u equals. If not, then I move on to trig. And if I had a trig, then that would be my u equals. And then if not, I would move on. So exponential is the last choice for a u equals. You only do that if you have no other choices. You don't really want u equal e to the x. That's never going to help you. So this is always going to be my choice for u. So for example, those previous two problems that we just did, that first one I had a 2x and an e to the 3x. That was an algebraic and an exponential. If I follow Liate, I had no logs. I had no inverse trig. A was algebraic. I had algebraic. I had to choose algebraic to be my u equals. Okay, same thing here. I have for part B there, I had an x and a sine. Log. Nope, no log. So then I move on. Inverse trig. Nope, no inverse trig. So I move on. Algebraic. Oh, I had an algebraic, so I had to let my u be the algebraic. Same thing here. I have an x and an ln. Logs. Oh, I have a log. So I have to, you have no choice. I have to let u be the ln. And then dv is always going to be just the other one. Pretty much every single time, just the other one, whatever that is. So that was my x and dx then would be my dv. Remember, product is commutative, so it doesn't matter the order that you multiply those two. And then I do the same thing. Now I have the decision, then I just follow through with the integration by parts, which is I need a du, the derivative of ln is 1 over x, and then I need a v, so the antiderivative of x is x squared over 2. Don't worry about the plus c until the end, but make sure you remember that plus c. And now I'm going to go through and get an answer here. So this is equal to, I'm going to copy the formula down one more time. It's uv minus the integral of v times du. I got to remember that formula here. Then I plug and chug. So u was ln of x, v was x squared over 2 minus the integral of v times du. And then I'm going to go on and just simplify first and then do the integral. I still highly recommend you do that simplification first and then the integral. That'll always be a little bit easier. So I'm going to rewrite that to become x squared over 2 ln of x minus the 1/2 is a constant multiple. I can leave that on the outside of the integral. And then x squared over x, one of those x's canceled. Now I can do the integral. So my answer was x squared over 2 times ln of x minus 1/2. And the integral of x is x squared over 2. So then, of course, that's going to become a 1/4 x squared. Don't forget your plus c. Ta-da! All right. Let's do a little bit more. That's my integration by parts. We just got to keep practicing. You should always be thinking of Liate because that's going to be your choice for the u equals. So for this part D, this next one, I have an x, a sine, and a cosine. I have an x, a sine, and a cosine, which does make that a little bit trickier for sure, but we can do it. We can definitely do this one. Do I have a log? No, I don't. So I can't do that one. Do I have an inverse trig? No. Do I have an algebraic? I do. X is my algebraic. So for that one, we got it. This is going to be a little bit trickier. My u would be x, which means dv has to be the other one, whatever it is. And yeah, in this case, it's uglier. Sine of x times cosine of x dx. dv sometimes is the uglier one. And in this case, it had another product. It's a little bit harder. We can do it. The process is the same. So du, the derivative of x is 1 dx. And then v, I need an antiderivative. So I'm going to zoom in here a little bit and I'm going to focus on the antiderivative of sine times cosine. And I'm going to do this in a little bit different color here. I'm going to just actually write down what it is that I'm looking for to remind me that I'm doing an antiderivative on indefinite integral. Now, I don't know the antiderivative of sine times cosine. I do know that it's a product. So I could do integration by parts right here. Or you don't want to start with integration by parts. You want to think of it in the order that you learned it. And in this case, I can do u sub. And I learned u sub earlier, so we should make sure we do a u sub here. If you think of it in the order you learned it, it'll be easier to keep track of. So I'm going to have to do a u sub here. I'm gonna let you, I guess I could call it U. I just already used the letter U over here, so I find that confusing. So I'm just choosing a different letter. So I'm just gonna choose W. You could choose Q. It doesn't matter. I would let my U be or my W be sine of X. And then dW is the cosine of X dx. So that takes care of that. And then this guy becomes the integral of U, not U. Of course, I chose the letter W times dW, which of course is 1/2 W squared. Remember, I told you we can throw in the plus C at the end of the problem. So then I have a 1/2 times sine of X squared is what I have there. Cool. So far, so good. This one's definitely a little bit trickier. I know I'm going to run out of space on this one. So I'm going to actually, sorry about that, give us a little bit more space. I just know I'm going to run out of space. So I'm going to copy all of this down. Sorry about that. Should have thought that through. There we go. And I'm going to go from here. Okay. All right, let's keep going. All right, so now I have my U, du, my dv, and my v. I'm going to go through and see what I have. So this is going to become, remember the formula is uv minus the integral of v times du. The way I learned it, this is up to you, was ultraviolet voodoo. I don't know why. My calculus professor said it that way, and so it kind of stuck in my head. But either way, you just have to know that formula. So now I get to plug and chug. My u was x, dv was 1/2 sine of x squared minus the integral of 1/2 sine of x squared times du, which was my dx. And then I have to simplify this. This is going to become 1/2 x times sine squared of x minus 1/2 times the integral of sine squared of x dx. And now this is where it's trickier. We can do it. This one's really a trig problem now. So I have to remind you of a couple of trig identities. We really got to know our trig identities from your trig classes. So let's think about those trig identities. One of them in particular was cosine squared of theta is 1 plus cosine of 2 theta over 2. Another one was sine squared of theta is 1 minus cosine of 2 theta divided by 2. These are going to be helpful formulas in integrating. So let's do this. What this is going to become 1/2 x times sine squared of x minus 1/2 times the integral of 1 minus cosine of 2x. I'm just simplifying that guy became 1 minus cosine of 2x, sorry, over 2. Instead of a theta, I had an x, but I just used that trig identity. Don't forget your differential. This is going to simplify even farther. 1/2 x sine squared of x minus 1/4, because I can take the constant multiples outside the integral. And then I can do the integral. Remember, you have to keep going because you can't have an integral in the answer. So you keep going until you've done all of the integration. And that's why this is a little bit more challenging. So now I have 1/2 x times sine squared of x minus 1/4 is on the outside of the integral. So it should be on the outside of that parentheses. And then the antiderivative of 1 is x minus the antiderivative of cosine is sine. But don't forget to divide by the constant multiple plus c. And then last but not least, 1/2 x times sine squared of x minus 1/4 x minus, plus, I'm distributing, plus 1/8 sine of 2x plus c. Ta-da! A bit trickier, huh? A bit trickier. Okay, I have another one that I want to think about really quick. That one's definitely trickier. Feel free to pause and rewind if you need. But while I'm right here, I have another kind of side note. Okay, so just a side note, not part of one of the examples, a trick, if you will. This trick that I'm about to show you does not always work, by the way. So just as a FYI, it does not always work. But I just want to come up with a quick other example really quick. Let's do the integral of 2x times e to the 3x. Now I could go through and choose my u and choose my dv, but I'm not gonna. I'm gonna show you a trick. This trick doesn't always work, by the way. This trick does not always work. Oh no, did it freeze? Hold on, Mike. My video is frozen. I don't know if this is still recording now. course it's not. Yeah. Maybe it is. Is it still recording? Let's see. Resume share. It looks like it's still recording. So I think I'm going to keep going. And I apologize for, of course, whatever issue that's you're seeing in the video. I'm sorry about it. My camera, my multiple monitors kind of screwed up there for a second. So I'm going to keep going because it looks like it's still recording, but I do apologize for that. Okay, so I know we already solved this problem, but we are going to solve it another way. So if you can, you're still gonna follow Liate every single time, always follow that. So this problem, do I have a log? If I do, I have to let that be the u equals. Nope, so I move on. Do I have an inverse trig? If I do, then that has to be my u equals. I don't, so I move on. A is algebraic. Do I have an algebraic? I do. So in this case, if I follow my Liate, u has to be 2x. And not only that, once I've decided that, does my u, if I were to take a bunch of derivatives of that u, will it eventually go to 0? And it will. That's the only time this trick is about to work. So this is called the tabular method. I'm going to write that down. This is called the tabular method, and it only works in this special case that I'm showing you like this. I'm going to do a little table here. That's why it's called tabular method. My u had to be 2x, and then I just do derivatives until I run out. This doesn't always work. If you never get to 0 when you do derivatives, then you cannot do this trick. You have to do the other way. I promise you. This trick only works if the derivative of u eventually goes to 0. And then my dv, I have to fill in the chart. My dv had to have been an e to the 3x. And then I do antiderivatives on the other side. So the antiderivative, in this case, the antiderivative of e to the 3x is e to the 3x, but divided by 3. And then another antiderivative, which of course I've written wrong there, is 1/9 e to the 3x because I had to divide by that constant multiple again. And then you get to do what's this diagonal multiplication with this extra plus minus until you run out. And then that actually just skips straight to the answer, which I just think is really cool. So it's going to be the 2x times 1/3 e to the 3x. That was that first diagonal multiplication. And then I have to go a -2. I had to throw in that extra negative. Every other one gets an extra negative. If this was already negative, then this would have turned positive. Keep that in mind. So then I would just go a -2 times 1/9 e to the 3x plus c. Ta-da. And if you want to see how cool that is, go back to the very first problem that we solved. That was the exact answer. We just did it the long way. So this was the long way, and now I'm showing you the tabular method, which is a shortcut. The shortcut does not always work. It only works if your u equals will have a derivative that eventually goes to 0. Just kind of a cool little method. And you're always allowed to use that method if it works. Which, for example, like this part C, would have been impossible. This was part C, we solved that one the shortest possible way. Because my u was ln, and the derivative of ln, no matter how many derivatives I took, would never go to 0. So the whole point of that tabular method is it only works if the derivative eventually goes to 0. So let's practice. I know I kind of scrolled a lot here because we were running out of space, so let's keep practicing. I'm going to do part E. So I still have to think of Liate. You still have to follow Liate. This is still step 1. So do I have a log? Nope. So then I move on. Do I have an inverse trig? Nope. So then I move on. Do I have an algebraic? Yes, I do. So that means in this case that my u has to be x squared. Then I can decide, do I get to use the shortcut or do I have to do the long way? Sometimes you're going to have to do the long way. But in this case, that derivative will eventually, if I keep taking derivatives, that derivative does eventually go to 0. So that is going to be my u equals. I like to organize my table like that. Here's my u, and then dv is going to have to be the other one, so the cosine of 2x. And then it's really important, once you do the derivatives on one side, you have to remember you are doing antiderivatives on the other side. So to do an antiderivative of cosine, the antiderivative of cosine is sine. but divided by the constant multiple. The antiderivative of sine is negative cosine, but divided by that constant multiple. And then the antiderivative of cosine is sine, but divided by that constant multiple. So be careful with your derivatives versus antiderivatives. We got to know those. You really have to practice. You have to have that in your head. Then I can just do my diagonal multiplication. So diagonal multiplication with an extra plus minus until you run out. That's why I do that dot, because you're going to run out eventually. In this case, I just ran out. So, and then I'm going to go ahead and go from here. This is going to become x squared times 1/2 sine of 2x. And then a negative 2x times a negative 1/4 cosine of 2x. And then a positive 2 times a negative 1/8 sine of 2x plus c. And then simplify. Okay, so 1/2 x squared sine of 2x plus 1/2 x cosine of 2x minus 1/4 sine of 2x plus c. Ta-da! Okay, we need practice. This is a lot. I know there's a lot going on in this section, but I'm telling you, I'm going to do one of every type in this video. That's my goal, is to do one of every type for you. So let's do part F of this example that we're working on. So just another example, the integral of x squared times ln squared of x. You have to follow Liate. You have to, non-negotiable. Start with L. Do you have a log? I do. So I have to let my u be the log spiel. Now I could try to take that derivative, and that derivative will never go to 0, so I don't get to do the shortcut. I have to do the regular way. So I have my choice for u, then dv is going to be the other one. I know you wanted this to be your u. I know you wanted it to, because then you could do the shortcut. Too bad, it wouldn't work. It really wouldn't work, because you have to let you have to follow Liate in order to use this integration by parts. If you tried this to be your u, then that would have to be a dv, but I don't know the antiderivative of ln squared. It is impossible, so I wouldn't be able to do it. So that's really what it comes down to. All right, so then now I've made that choice. Then my du, the derivative of ln squared, is bring the 2 down, leave the inside the same, times the derivative of the inside. That was a chain rule. And then the antiderivative of this one was x cubed over 3. We'll deal with the plus c later. And then this guy is going to become, actually, I think I'll just go down because I'll have enough space right here. So then this is going to become u, maybe I'll just write the formula up here, uv minus the integral of v times du. Okay, so u, which was ln squared, times v, which is x cubed over 3, minus the integral of x cubed over 3 times 2 ln of x times 1 over x dx. And then, don't forget this part, simplify first and then integrate. So minus 2/3, it looks like, take the constants outside the integral, and then I have an x squared ln of x dx. Okay, I simplified. Now I have to go through from here and try to do the integral. So now I'm going to just give myself a little bit more space. Okay, so I'm going to zoom in so that we can see where we're at. This is where I'm at right now. This guy is good because it doesn't have an integral, so we're good. This guy has an integral. I need to find its antiderivative. Do you know this antiderivative right now off the top of your head? No. Could I do a u sub? You could try. Pause, give it a try. It won't work. It's a product. I have no other choice. I've got to do integration by parts again. Oftentimes you have to do integration by parts twice in one problem. So same thing, follow Liate. You have no choice. U has to be that ln. dv will have to be the other one. And then I do the same thing. du would be 1 over x dx. V would be the antiderivative, which is x cubed over 3. Here's the tricky part. Make sure that if you need a pause to catch up, do so. Pause the video so you can catch up. And then make sure that what you have written is exactly like this. The notation is very, very important. There's no other way. You have to keep one equal sign on top of the other. Otherwise, it's not a true equal sign. So x cubed over 3, ln squared of x minus 2/3. I don't get to lose any of that stuff. That was part of the thing. I can't lose any of it. I can't. Then I have this integral. That integral is using integration by parts. So then that entire integral turns into a parentheses with its own integration by parts. So I'm going to fill in from there, uv minus the integral of v times du. So ln of x times x cubed over 3 minus the integral of x cubed over 3 times 1 over x dx. And then simplify, okay, we can do it. This is going to become x cubed over 3 times ln squared of x minus 2/9 x cubed ln of x plus 2/9 times the integral of x squared dx. I distributed the negative 2/3 and simplified. Then I can go ahead and get a final answer here. I have x cubed over 3 times ln squared of x minus 2/9 x cubed ln of x. You need to write one on top of the other. Don't go to the side, especially in this online class. You're going to have to take a picture of your work and send it to me. I need to be able to visualize it and see what you're talking about. So it's got to be clear. Plus 2 over, and then when I did the antiderivative of x squared, it was x cubed over 3. So I had an extra 3 on the bottom. Don't forget your plus c. Ta-da! So a lot of the times you are going to end up having to do integration by parts twice. Just be aware of that. Okay, let's do another one. So same kind of thing. So next example, this one is another one that's going to be a little bit trickier. Oh, sorry about that. So it's going to take some time. It's also going to take some space. Okay, so be aware of that as you're taking notes. Okay, we can do it. Same thing, follow Liate. Do I have a log? Nope. Do I have an inverse trig? Nope. Do I have an algebraic? Nope. Do I have Liate? Do I have a t? Oh, I do. T for trig. Okay, so then I would let my u be the trig. So u has to be cosine of 4x, and then I can decide, do I get to do the shortcut? Will this derivative, if I take a bunch of derivatives, second derivative, third derivative, over and over again, will it ever go to 0? Nope, it's going to go sine, cosine, plus minus. It's never going to go to 0. So I can't do the shortcut. Oh, well. About half the time you get to do the shortcut. I'd say it's about half, give or take. So for real, sometimes you just can't use it. So then dv has to be the other one, which is e to the 2x, e to the negative 2x dx. And then I need a du next. So the derivative of cosine is negative sine. And that one, remember, you did a derivative. So you multiplied by the derivative of the inside. That was a chain rule. That was not an antiderivative. That's why it's times 4. And then this one is an antiderivative. So that's why I did divide by the constant multiple. And remember, we'll throw the plus c's in later. Okay, so then this guy is going to become equal to, I have a uv, maybe I should write it down one more time, uv minus the integral of v times du. You have to have that memorized, uv minus the integral of v times du. All right, so then I'm going to have my u, which was cosine of 4x, times negative 1/2 e to the negative 2x, minus the integral of negative 1/2 e to the negative 2x, times negative 4 sine of 4x dx. It looks like I forgot my differential earlier, so I'll add that in. And then simplify, make sure we simplify here. So this is negative 1/2 cosine of 4x e to the negative 2x minus 2 times the integral of e to the negative 2x times sine of 4x dx. Take your time, pause if you need to, think it through. This one's a hard one. I promise you, this one's kind of a tricky one. Okay, all right. So we're not done though, right? Now I got to do the integral. So I have to do the integral of this guy. Again, it's another product. No amount of u sub is going to help me. So yeah, I have to do integration by parts again. I'm going to zoom in. Let's do it. I'm going to let my u still follow Liate. Non-negotiable. Do I have a log? No. Do I have an inverse trig? No. Do I have an algebraic? No. Do I have a trig? I do. Okay, so u is sine of 4x. So dv has to be the other one. And so then du, the derivative of sine, is cosine, but don't forget to multiply by the derivative of the inside. And then the antiderivative here, nice and easy there. Then I'm going to have its own integration by parts. So there's still going to be a negative 2 in front of that integral. And then that entire integral needs to turn into a parentheses, and it's going to have its own integration by parts, which was uv minus the integral of v times du. So I fill that in. You now hopefully have it memorized, which is u times dv, which was negative 1/2 e to the negative 2x, minus the integral of v times du. So 4 cosine of 4x dx. There's a dx there. There we go. And a parentheses. And then I have to zoom out, and hopefully you guys can see this on your page as you're taking notes. Don't forget, you still had an equal sign over here. You cannot lose that equal sign. It will be impossible to keep track of everything. So you can't really do integration in your head. You could probably do u sub in your head. That's probably about as much as you can do in your head. That's about it. It's way too complicated to do this whole thing in your head. So make sure you keep that equal sign. If you're not doing it in your head, then that means all of it has to be written down. Don't lose it. Okay, then I simplify. This is going to become, I have a negative 1/2 cosine of 4x e to the negative 2x plus sine of 4x e to the negative 2x. I'm distributing along the way. Minus a 4 times the integral of e to the negative 2x times cosine of 4x dx. Let me check. Let's point out what it is that I did and keep track of things. Maybe I've not done it all correctly. I'm distributing. So that's why that negative 2 and negative 1/2 turn into a positive. Those two negatives canceled. And this became 1/2 times 4, which is 2. And then I multiplied it by that negative 2, which is where I got that negative 4 from. Cool. Okay, then I got to do this again. You keep going until you don't have any more integrals. So could I just do that again? Yeah, I could do another integration by parts, but you can see how that is going to go on forever. And this is cyclical. I don't want to do that forever. That's crazy. So you always want to look at the bigger picture, which is why it's so important that you have everything on your piece of paper, including all of the equal signs. It would be impossible if you had this written down in any other way. You got to keep track of your equal signs. So in the original problem was the integral of e to the negative 2x times cosine. I now have the original problem in my answer. So let's be really clear with that. Let's write down what the original problem was, because that was always on the other side of that equal sign, e to the negative 2x cosine of 4x dx. And now if I think about it, I can just solve for my unknown. I can combine like terms. I can take this whole thing and bring it to the other side of that equal sign. I can add 4 of that integral to the other side of that equal sign. Don't forget to keep both sides of that equal sign nice and organized. Try not to lose anything. And then I can divide everything by 5, and that'll get the answer to the question. So my original question was e to the integral of e to the negative 2x times cosine of 4x dx. If I divided everything by 5, I got negative 1/10 cosine of 4x times e to the negative 2x plus 1/5 sine of 4x e to the negative 2x. And of course, don't forget your plus c at the end. Ta-da! Excellent. A bit trickier. I would say more than just a bit. I would say very tricky for sure, definitely. Okay, let's do a little bit more. I'm not going to be able to solve every single one of these problems, but I am going to keep going and do a few more. The next few I'm going to do is what if I have bounds? Right? What if this were a definite integral? Well, a definite integral should feel fairly obvious. You do the exact same thing, but you just no longer have a plus c and you have your bounds. So let's practice those. So here's another example, the integral from 1 to 3 of ln of x. You still have to follow Liate. You still have to. I have a log. I have no choice. So my u would be ln of x, and dv is the other one. This one's kind of weird. It doesn't feel like there's another one. There is. The other one is dx. That's a 1 times dx. It really is a 1 times dx. And if you think of it that way, the derivatives will be easier to find, or the integral will be easier to find. The antiderivative of 1 is just x. And then I'm still going to do my uv minus the integral of v times du. We can do it. So u was ln of x times x minus the integral of x times 1 over x dx. And here's the correct notation. There's more than one way. I'm going to give you the easiest notation, the least amount of things to write down. With your bounds, just do one big giant parentheses, 1 and 3. Because then you can just plug in those bounds at the end. You have to keep them. You can't lose them. You're not, otherwise, if I didn't write that from 1 to 3, then this is not a true equal sign. You have to keep it. It's incorrect without it, but at least it's at the end, and we'll deal with it later. So then this becomes x times ln of x. I don't know why. I just think that looks prettier. It doesn't matter. Minus the integral of 1 dx because the x canceled. So then this becomes x times ln of x minus x evaluated from 1 to 3. So then I'm just going to plug some stuff in, and that'll be 3 times ln of 3 minus 3 minus 1 times ln of 1 minus 1. So 3 ln of 3 minus 3. Ln of 1 is 0, so plus 1. 3 ln of 3 minus 2. Ta-da! Integration by parts. This is a really, really big one. It shows up a lot, so make sure that you feel comfortable with this one. After you do the practice, you might want to rewatch a video or two. This one just shows up everywhere. Let's do another one. The integral from 0 to pi of x times sine of x dx. I'm going to do Liate. Do I have a log? No. Do I have an I? Is it inverse trig? No. Do I have an algebraic? I do. My algebraic is x, and x is something that its derivative will eventually go down to 0. So in fact, I get to do the tabular method. So if my u is x, then its derivative eventually went down to 0. And then you fill in the chart with antiderivatives. Don't forget that. The antiderivative of sine is negative cosine. The antiderivative of negative cosine is negative sine. And then I'm going to do the diagonal multiplication with the plus minus until I run out. And so then this then becomes equal to x times negative cosine of x, and then a negative 1 times a negative sine of x, right? In that case, those two negatives here and here canceled. And then, of course, that whole thing, I don't have a plus c here, so evaluated from 0 to pi, negative pi cosine of pi plus sine of pi minus negative 0 times cosine of 0 plus sine of 0. Feel free to use your calculator if you need, but I hope you know some of those ones. Cosine of pi is negative 1. I had to think about it. Maybe I should have used my calculator, but cosine of pi is negative 1, yes, and then plus sine of pi is 0. Yeah, man, I really have to think about it. And then the last little bit also ended up going to 0. So because 0 and sine of 0 is 0, pi. Ta-da. Okay. All right, we're on a roll. I know it's kind of a lot. There's definitely plenty to do for this one. Let's practice another one that has an inverse trig. This is one that we haven't done yet so far. So let's do that one. Still follow Liate. If I have a log, I have to let that be the u equals. I don't, so I move on. I was inverse trig. Do I have an inverse trig? I do. I do. So then I have to let my u be the inverse trig here. So let's go ahead and do that. U is going to be the sine inverse. dv is going to be the other one. And then I need to do the derivative of sine inverse, which you still need to know from Calc 1. The derivative of sine inverse is 1 over the square root of 1 minus x squared dx. Okay, good. And then the antiderivative of dx was just x. Sorry about the recording being weird too. I have multiple monitors, and since it froze, I don't know where the camera is anymore. So I apologize. But hopefully you can still see this at least. Let's do the integration by parts now. This is going to become, I know I'm going to run out of space, so I'm going to kind of make that a little bit smaller. This is going to become uv minus the integral of v times du. So this becomes x times sine inverse of x minus the integral of x times 1 over the square root of 1 minus x squared dx. And then I'm going to simplify x times, and you can write it if you prefer as arc sine of x. I don't have a preference so long as it's clear. Make sure your handwriting is clear. I have to be able to see it. Minus the integral of x times 1 minus x squared to the power of negative 1/2 dx. And then I keep going until I don't have an integral anymore, right? This one actually I can use a u sub for though. So I'm going to do that. U is equal to 1 minus x squared. Du is negative 2x dx. So du divided by negative 2 is x dx. This is kind of a long one. This is going to then become x times arc sine of x minus the integral of u to the negative 1/2 times du divided by -2. If you still need help with use, make sure you keep practicing. Come to my office hours, email me, something like that. Then this is x times arc sine of x plus 1/2. The two negatives cancel, then I take the 1/2 outside the integral, and then I'm going to add 1 to the power, divide by the new power. And then I'm going to replace that. So now I have x times arc sine of x plus the square root of u, which is 1 minus x squared. And I think this one had bounds. I'm so sorry. I think I forgot the bounds the whole time. It was 1/2 and √3/2. Okay, so I should have kept those bounds the whole time. Yeah, I got to be careful with that notation. Kept those bounds the whole time so I don't lose those bounds. Okay, now we can plug and chug. So this will become the square root of 3/2 times arc sine of the square root of 3/2. And arc sine of the square root of 3/2 is pi-thirds. We should know from our unit circle. Okay, plus the square root of 1 minus the square root of 3/2 squared. Okay, minus, and then I'm going to plug in 1/2. 1/2 arc sine of 1/2 is pi/6. And then plus the square root of 1 minus 1/2 squared. And then you could simplify, combine your like terms, pi√3/6 plus 1 minus 3/4 is 1/4, and the square root of 1/4 is 1/2. Okay, and then I have minus, then that became a pi/12, plus, I might as well just distribute that negative and make that, make that a minus, the square root of 3/4. Ta-da! I suppose I could combine some more, get a common denominator if I want to, but I don't think that's necessary. Ta-da! All right, let's skip around a little bit. I won't be able to solve all of these problems just because there's so many, lots and lots of practice along the way, but I am going to skip around a little bit to some of word problems here. These are going to go back to the volumes of revolution. So let's do an example. I want to find the volume of the solid that is generated when the region is revolved as described. The region bounded by e to the negative x, x equals ln of 2, and the coordinate axes. When I say coordinate axes, that's plural. That means both the x and the y-axis is revolved about the y-axis. So let's try to do that. Remember, anytime you're trying to find a volume, your step 1 is to draw a picture. Your step 1 is to draw a picture. So e to the minus x, I hope we know what that looks like. If you need your graphing calculator, go for it. That's maybe not the greatest picture, but it was kind of like that. It's about the same. That's okay. Here's my f of x is e to the negative x. X equals ln of 2 is a vertical line. Here, ln of 2 is a number. You can type it into your calculator if you want a decimal. Here is my region R, and I would like to revolve that region about the y-axis. Okay, let me zoom in. Remember, when you're doing volumes of revolution, you get to pick the sliver, but the sliver chooses the method. So if I choose this, let's say horizontal sliver, which is the dy sliver, remember there are infinitely many slivers. So the problem here is that some of them have the purple graph, which is the exponential on top, and some of them have the red graph, which is the vertical line on top. That's too many integrals. I don't want to do that. So I'm going to choose the other sliver. I'm going to choose my dx sliver, which is vertical. And I want to remember revolve that around the y-axis. So as I revolve that all the way around, the sliver is choosing the method. And it looks like in this case, that sliver chose a shell method because that's a cylinder. So in this case, I'm going to do the shell method. All right, so now we have an idea of what I'm doing. Here is my shell volume for shell method was 2 pi times the integral of x times the height of that guy was e to the negative x dx. And I'm going from 0 to ln of 2. You might want to go back to visit some shell method problems if you want. Okay, then I integrate. This is a perfect problem that is showing up right here because I don't know how to integrate that one, but I do know now because I can use integration by parts. This is an example where I can do the shortcut, so I'm going to. My u ended up being x, and its derivative was 1, and its derivative was 0. So then antiderivatives on the other side to fill in the chart. Diagonal multiplication with the extra plus minus plus minus plus minus until you run out. So then this becomes equals 2 pi times, don't forget that parentheses, the integral turns into the parentheses, x times negative e to the negative x minus 1 times e to the negative x, evaluated from 0 to ln of 2. And then I plug in my bounds, 2 pi times negative ln of 2, e to the negative ln of 2 minus e to the negative ln of 2, and then minus 2 pi times, if I plug in 0, I got 0 minus e to the 0. And then I'm going to simplify. So 2 pi times negative ln of 2. I'm going to highlight this really quick. So maybe pause what you're writing and watch for a second. E to the negative ln of 2. This negative can come up as an exponent and make that a 1/2. So then the e and ln cancels, and that just becomes 1/2 minus 1/2 minus 2 pi times e to the 0 is 1. So that became a -1, which turned that into a positive. And then I'm suppose you can distribute that 2 pi if you'd really like. I don't think that's necessary though, but you could. Ta-da! All right, so there's definitely plenty of them. I won't be able to do all of them though. So practice the other one as well. Practice that second example. I think that's going to be the most helpful for you guys to get a good understanding of it. If you have questions, let me know. That's all there is for 3.2. See you next time. Or 3.1, sorry. See you next time. Thanks.